Okay, first question. Current is the flow of charge. So we have a situation where steady current of 2.5 amps exists in a wire for 4 minutes. We want to know what total charge passes through the wire and how many electrons would this be. So, diagram of a wire, we have 2.5 amps. So again, 2.5 amps, that would be coulombs per second. And the current flows for 4 minutes, which we know is 240 seconds. We're used to using seconds, of course. So, total charge, we have this formula, it's sort of the definition of current, and that's charge per time. So in solving for Q, remember Q is for charge, our variable. In solving for Q, we're going to multiply the current by the time. 2.5 amps times 240 seconds is 600 coulombs. That's a huge amount of charge. Ouch. B, so how many electrons is 600 coulombs? It's going to be a whole lot. This is our conversion factor. We know that the charge on an electron is 1.6 times 10 to the negative 19 coulombs. So we start with the information we know because coulombs are here. We're going to put coulombs down here so they cancel, leaving us with units of electrons. And after dividing, we end up with something like 3.8 times 10 to the 21st electrons. Muchos. Question 2, or 18.4. Current and potential. So again, potential is voltage, alright, and you are familiar with voltage a little bit. Current I enters a resistor R as shown in figure 18.13. Is the potential higher at point A or at point B? Is the current greater at point A or point B? So I drew this and I included a battery just so we can sort of conceptualize what's happening. So again, the battery, this side would be positive, this side would be negative. We say that the current flows this way, even though we know that it's actually electrons going this way. And I know that's weird, but that's what we do. So let's say, for example, that this is a 12-volt battery, and that this is a 6-ohm resistor, whatever it is, a light bulb or a toaster or something like that. So we have this 12-volt battery. I suppose you wouldn't be running a toaster off a battery, but whatever. So what happens is the battery's pushing the electrons, pushes the electrons, pushes the electrons, pushes the electrons, and this is where they experience the resistance. We say that wires, we idealize and say the wires have zero resistance. So it's like a ball rolling along some flat ground. This would be like a ball rolling uphill. You have to push it to get uphill. So once the electrons pass through the resistor, they basically need no voltage in order to make it back to the battery. So what we say is that if we were using formulas and we said V equals IR, we would say 12 equals current times resistance, and we get that the current is 2 amps. So when we have something like the current is 2 amps, what that means is that the current everywhere in the circuit is 2 amps. The current at point A, the current at point B, the current passing through the resistor, the current right before the battery, or the current right after the battery. You're never going to have a situation, I mean, there is this thing called a capacitor, but we won't really get to those. You're never going to have electrons bunch up in some part of the circuit. If the current is this here, it's going to be the same over here. So the current would be the same. So where is the current highest? Well, it's the same at both A and B. But in terms of the potential or the voltage, so it's getting a little messy here. Whoops. So all these electrons have a potential of 12 volts because they just left the battery and they're moving along and they're cruising and they're cruising and they're cruising. All of that potential is used up in getting through the resistor. By the time they're through the resistor, they have zero potential, and they just kind of scoot along the wire because there's no resistance back to the battery. So the potential would be 12 volts here, and it would be 0 volts here. We say that the voltage drop across the resistor is 12 volts. All of the voltage of the battery is used up across the resistor. So potential is highest at point A. Okay. And then some calculating here. So suppose you want to connect your stereo to remote speakers, meaning far away, 20 meters. If each wire must be 20 meters long, what diameter copper wire should you use to keep the resistance less than 0.1 ohm per wire? So the longer the wire is, the more resistance it's going to offer. And right down here, I was saying, well, we say that the wires have no resistance. And that's a good approximation. So relative to the speakers, these have very negligible resistance. But the reality is that they do have some. So if we look on, well, let me finish reading the question, sorry. If each wire must be 20 meters long, what diameter copper wire should you use to keep the resistance less than 0.1 ohms per wire? So first of all, that's copper, so we know the resistivity of copper. And we're looking for area, and we know length. If the current to each speaker is 4 amps, what is the potential difference or voltage drop across each wire? So, somewhere I wrote this. Aha! So, 18.5. We assume that wires have no resistance, but the reality is that they do have some. So, this is our formula for the resistance of some wire, or the material has a resistivity. What's that variable called? Yeah, rho. If you look at page 508, we see that the resistivity for copper is 1.68 times 10 to the negative 8th. I left the units off here. The units are whatever it has to be so that we get ohms over here, and this is meters, and this is meters squared. The length of the wire is 20, and the area is pi r squared. We're actually looking for diameter, but we'll do that as the last step. And we know that, excuse me, that the resistance has to be 0.1 ohms or less. So if we do some solving, I think I multiplied by r squared, I divided by 0.1, take the square root to get radius. So square root that to get radius, multiply by 2 to get diameter, and we should end up with this, which is 2.1 millimeters, which is reasonable for the diameter of a wire. If you get some fancy amp and big booming subwoofer in your car, there's going to be these big fat wires. Like, I think I got some and they were almost a centimeter in diameter, because there's a lot of current that has to go to that. Okay, B, what was it? Oh yeah. So if there's a current of 4 amps through the wire, what is the voltage drop across the wire? So we're using, this is one version of Ohm's law. Voltage equals current times resistance, and we end up with 0.4 volts. So again, minimal compared to the speaker, but it is something. That's my speaker. Alright, next page. So, how to connect a battery. What is wrong with each of these schemes shown for lighting a flashlight bulb with a flashlight battery with a single wire? So, this, in order for the electrons, the current to flow, it has to go from, so here I am saying that the current goes from the positive, right? Conventional current. It has to go from the positive through the device and then back to the negative side. So here, and with a, excuse me, with a light bulb, this right here is one terminal and this right here is another terminal, just so you know, and we'll see that in class. But in order for this, in order for current to flow, there need to be something connecting that to this. So what do I say? Not a complete circuit, no wire from negative terminal of battery. And in part B, sure, we have both terminals of the bulb connected, but they're just connected to the positive side of the battery. One has to go back to the other, as in example C. So that was a tricky question. There's nothing wrong here. The current will flow. It is a complete circuit. So from the positive terminal, it goes right into one terminal of the battery, and then from the other terminal of the battery back to the negative. So we have light being emitted from the light bulb. Okay, and then I threw this diagram in here. You've seen this switch, and it took me a while to figure it out. But I remember it's O for open circuit, and then this is a closed circuit, so this means that this is in English, not in science. This is on, and this is off. So now that you've seen it, you'll see these all over the place and go, dude, that's what that means. All right. Okay. Last question. Stretching changes resistance. So we're assuming we have some big fat wire like this and we're going to stretch it. Metal does have these properties. It's ductile, meaning stretchable. So this would have a low resistance, this would have a high resistance. One, because it's longer, and because it's thinner. Remember the kids running through the hallway example? Okay. So here's what we're thinking about. Resistance is resistivity times length divided by area. So it's the same material. We have this material and we're just stretching it out. So when we say it's the same material, we mean that the volume remains constant. So if our volume remains constant, over here, the volume of this would be the base times the height, so the area times the length. And over here, it would be the length times this area, and it would have to be constant. So in order for LA to equal 2L something A, I'm hoping you can recognize that that would be like that. So the 2 and the 1/2 would cancel, and we'd have LA equals LA. So if we stretch this out so that it's twice the length, the area would be half as much. So in our formula here, we would have the resistivity is the same for both. It's the same material. The length turned into 2 length, and the area turned into 1/2 area. And you know that 2 divided by 1/2 is 4. So this would have 4 times the resistance than this. So this would be like 1R, and this would be 4R. Okay, that's it.